Himalayan pink salt doesn't grow or cook into existence inside a factory. It's an ancient rock salt deposit that gets mined like stone, then refined with mechanical separation, washing, drying, and grading until it meets food and export standards. The pink color is not dye and not magic tits, mostly trace iron compounds, along with small amounts of other minerals trapped in the crystal lattice and in microscopic inclusions. The story starts underground, because the quality of the final salt is decided by geology and mining method. Most commercial Himalayan pink salt comes from the salt range in Punjab, Pakistan, with the Khewra region being the best-known source. And the deposit formed when prehistoric seawater evaporated and was later buried and compressed. Over millions of years, the salt recrystallized into thick rock layers, and small mineral impurities became locked in, creating white blush and deep pink bands that factories later separate and blend for consistent color. Modern extraction is designed to avoid collapsing the mine and to keep contamination low. A common layout is room and pillar mining, where large rooms are excavated while pillars of salt are left behind to support the roof. Instead of grabbing random rubble, operators selectively cut specific seams to meet different grades. Because darker veins can carry more non-salt inclusions, while very pale rock produces a cleaner, a whiter product that may not match the pink branding, cutting, and breaking. The rock can be done by drilling and controlled blasting, or by mechanical continuous miners with cutting heads that shave the salt face. Mechanical cutting reduces explosive residue risk and can give more uniform rock size, which improves downstream crushing efficiency. Dust is the constant enemy underground, so ventilation and dust suppression systems keep airborne salt particles from damaging equipment and affecting worker safety. Once extracted, rock salt moves out of the mine on conveyors or heavy haul vehicles, and the factory immediately treats it like a raw mineral, not a food. Incoming loads are weighed and lot-coded for traceability, because export customers want documentation linking each bag back to a mine section and production date. Visual inspection catches obvious clay seams in foreign rock, and magnets are often placed early in the line to capture steel fragments from drilling tools and conveyor wear. Primary crushing is where boulders become manageable feed for cleaning. Jaw crushers or gyratory crushers reduce rock to fist-sized chunks, and then hammer mills or roll crushers take it down further.
The transcription is currently unavailable. Please try again later.
Crusher selection is not cosmetic. Impact mills create more fines and dust, while roll crushers can produce a tighter size distribution with fewer powdery particles, which is useful when the goal is large grinder crystals. After crushing, Factories usually run screening and air separation to remove loose dust and very fine particles before washing. This matters because fines consume water, carry more surface contamination, and slow drying later. Vibratory screens split material into coarse, medium, and fine streams. And each stream can be processed differently depending on the final product lineup: coarse for grinders, medium for cooking salt, and fine for table salt or industrial applications. The biggest fork in the process is whether the plant uses dry processing or wet processing. Dry processing means the factory relies on mechanical sorting, screening, and sometimes optical color sorting, then packages salt with minimal water use. Wet processing means washing or dissolving and tree-crystallizing to remove insoluble impurities. And it produces a cleaner product, but at higher water and energy cost. In a wet line, crushed salt enters wash drums or screw washers where it's mixed with clean water or saturated brine. Factories often prefer brine washing instead of plain water because brine doesn't dissolve as much salt, reducing yield loss. The wash loosens clay, dust, and soluble surface residues, and the slurry passes over screens where insoluble dirt is removed. Hydrocyclones may follow to separate heavy grit from the salt crystals using centrifugal force, protecting pumps and preventing gritty texture in the final product. If the plant produces premium high-purity salt, it may go beyond washing and use a controlled dissolution step. The salt is dissolved into brine in mixing tanks, then filtered to remove insolubles, and then purified brine is evaporated to recrystallize salt. This is essentially running a salt refinery. Brine concentration, temperature, and filtration quality determine crystal purity and shape. Recrystallization costs more, but it yields consistent white tuple crystals that can be tinted by blending with pink fractions for a uniform brand color without relying on dirty inclusions. After washing, dewatering becomes critical because wet salt clumps and won't screen accurately. The plant uses centrifuges, vibratory dewatering screens, or screw presses to remove free water quickly.
Maintaining 100% natural purity, the Himalayan salt moves off the conveyor through a final step of sterilization.
Moisture control here is not optional. Too much moisture creates caking and storage silos, jams packaging machines, and causes weight drift in bags. Drying is where the factory spends serious energy, because salt holds water on its surface and in microcrevices even after dewatering. Rotary drum dryers or fluidized bed dryers push hot air through moving salt to drive moisture down to a tight target, often well below 1% depending on the product. Fluidized bed dryers are favored for uniform drying and high throughput, because salt particles behave like a boiling bed when air velocity is tuned correctly, exposing maximum surface area to hot air. Dryer control is a balance between speed and crystal integrity. Excessive temperature can fracture crystals and create more fines, which changes how the salt pours and how it looks in clear packaging. Sensors monitor inlet and outlet air temperature, product temperature, and exhaust humidity. And some plants use inline moisture analyzers to keep the dryer from drifting during long runs. Once dry, salt is graded like an industrial aggregate. Multi-deck vibratory screens separate precise size cuts, extra coarse chunks. Standard coarse for grinders, medium for culinary use, fine, and powder. Each cut has a different value. High-capacity plants tune screen mesh and vibration amplitude to maximize yield in the sizes that sell best. Fines aren't wasted. They're routed to milling systems for fine salt or compacted for lick blocks in industrial uses. Color control is part of the pink salt identity, so modern factories often add optical sorting. Cameras and sensors detect color and brightness, and air jets eject overly dark pieces, gray stones, or foreign fragments. Optical sorting is especially valuable because natural salt bands vary. A premium brand wants a consistent blush tone across every bag, not a mix of white crystals and deep red chunks. Milling is used when the factory makes fine culinary salt. Roller mills or pin mills reduce particle size. Then air classifiers remove ultrafine dust that would cause clumping and poor flow. Fine salt behaves differently than coarse crystals. It packs tighter, absorbs surface moisture faster, and bridges and hoppers, so the plant designs separate silos and feeding systems for each grade. Flowability is the next engineering hurdle, because consumers want salt that pours, not salt that bricks. Some products remain additive-free, meaning no anti-caking agents are used. But that requires stricter drying, tighter moisture control in packaging, and higher barrier bags. When allowed and desired, anti-caking agents like silicon dioxide or calcium silicate are blended in at very small percentages using microfeeders and ribbon blenders to prevent clumps without changing taste. Iodization is another decision point that changes the line. Many Himalayan pink salt products are sold non-iodized, even though iodized salt is a major public health tool in many countries. If iodization is required for a market, potassium iodate solution can be sprayed onto salt in a mixer, then dried lightly to fix it. Dosing must be extremely accurate because iodine levels are regulated, and iodine can degrade over time with heat and humidity. So packaging and storage become part of the compliance plan. Food safety and purity testing run alongside production because rock salt can contain soluble matter and trace metals depending on seam composition. Quality labs test for moisture, insoluble content, and particle size distribution. And they also run trace element analysis using techniques like XRF screening and ICP-MS for detailed heavy metal profiles. This matters because the marketing often implies health benefits from trace minerals. But in reality, those minerals are present in very small amounts and are not a reliable nutrition source. While contaminants must stay below legal limits, microbiology is usually a lower risk in salt because low water activity inhibits growth. But contamination can still happen through wet processing water, dirty conveyors, or packaging rooms. That's why facilities separate wet zones from dry zones, manage condensation aggressively, and sanitize equipment that contacts wet salt. Dust management is also a safety issue, because fine salt dust is corrosive to electronics and can irritate lungs. So, dust extraction and sealed bearings are standard on crushers, screens, and conveyors. Packaging is where bulk mineral becomes a retail-ready product, and it's engineered for both appearance and moisture protection. Coarse crystals often go into PET jars with grinder tops. The factory uses volumetric or whey filling with vibration control, so crystals settle consistently. Fine salt goes into pouches or cartons with precise net weight checks. And high-speed check weighers reject underfills and overfills to maintain compliance and cost control. Moisture barrier is a core requirement, especially for additive-free products. Films with low water vapor transmission rates prevent caking during ocean freight and warehouse storage. Many plants add desiccant packs in premium jars, not because salt spoils, because moisture pickup destroys permeability and triggers. Customer complaints. Inline inspection is standard in export-grade plants. Metal detectors and X-ray systems scan packaged product to catch foreign objects. And vision systems verify cap presence, label correctness, and readable lot codes. The lot code is not decoration. It ties every unit back to production records, including mine section, wash water parameters, dryer settings, and lab results. Waste and utility systems reveal how factory this process really is. Wash water is loaded with fine clay and dissolved salts. It's treated with settling tanks, filtration, and sometimes evaporative recovery, depending on local water constraints. Salt brine is corrosive, so piping, pumps, and valves are selected for corrosion resistance. And preventive maintenance is scheduled tightly because a small leak can destroy motors and bearings fast. Energy efficiency is engineered into drying and air handling. Rotary dryers can recover heat from exhaust, and fluidized bed systems often run with recirculated air to reduce fuel use. Variable frequency drives on fans and conveyors reduce power draw when throughput changes. And many facilities measure energy per ton as closely as they measure yield per ton. The full process comes down to transforming a geological material into a standardized consumer product. Mining provides the raw crystal. Crushing defines size and yield. Washing and purification define cleanliness. Drying defines flowability. Sorting defines appearance. And packaging defines shelf performance. The factory isn't creating pink salt. It's manufacturing consistency. So a rock that formed in ancient seas can arrive on a modern kitchen shelf as uniform crystals with predictable color. Low moisture, controlled impurities, and full traceability from underground seem to seal bag.